more slide on representations. So what we have discussed so far, the representations I just showed you, what we want to address there is the problem of how do we represent these models in the first place, right? And that substitutes for densities. Now the second representation problem that I mentioned earlier is how can we substitute for the base equation? Yeah? We need some way, if we can define these priors, we need some way to turn them into posteriors. How can we do that? And basically the solution that all non-parametric Bayesian models that you can find in the literature use, or almost all of them, is conjugacy. So we've already seen conjugacy a couple of times, and remember yesterday I said I defined conjugacy as a Bayesian model is conjugate if the posterior distribution is in the same class of distributions as the prior. And we saw that the Dirichlet process, for example, is conjugate because the posterior of a Dirichlet process is once again a Dirichlet process. Okay. Now, there's an extra subtlety here, because this so-called closure undersampling property, this definition of conjugacy, in non-parametric models is actually not quite enough to do what we want to do. Yeah? Because what we would like to do in the Dirichlet process case, what was the nice thing about the Dirichlet process, it was not simply that the posterior is again a Dirichlet process. The nice thing was that we know which Dirichlet process it is, right? So we had a formula which tells us how to compute, given from the observations that we have made, how to compute the parameter that specifies the posterior. That was this Dirichlet posterior process form, the Dirichlet process posterior formula. And so we need to distinguish two different types of conjugacy. One is what I've called, so I'm following work by terminology introduced by Antonio Leoy and Igor Prinster here, who call a model which is like this, in this general form conjugate, they call that structurally conjugate. Yeah, so that is simply this closure undersampling property. And then we can make a stronger requirement, and that is that there is some closed form update of the parameters, of the hyperparameters which specify the prior. Okay? So we have a class of priors, and each of them is specified by some hyperparameter. In the Dirichlet process case, those are the concentration parameter, the alpha, and this measure G0, this base measure, right? They specify which particular Dirichlet process we use as a prior. And now the form of conjugacy that we have there is we have the prior parameters, and we have the data, or the observations, and then we have a mapping which takes that to the posterior hyperparameters. Yeah? So that way we can compute the posterior, we can determine the posterior without actually using a Bayes equation. Yeah? Okay, and yeah, if you look that up in the work of Leoy and Prinster, they call this, I call this functional conjugacy, because I want to avoid confusion. In their book chapter, they call it parametric conjugacy. And you know, after I told you all about this distinction between parametric and non-parametric models, I don't want to introduce something as parametric conjugacy, which is really only important in non-parametric models. Okay? But basically, the notion, the idea why they call it non-parametric conjugacy is very simply because it updates the parameters. Yeah? So, but I will refer to it as functional conjugacy because we have a functional update for the parameters. Okay. Now, the Dirichlet process is an example of this case here, the Pittman-York process as well, the Gaussian process as well. So the update formulas for the Gaussian process posteriors that John showed you, these are a form of this functional conjugacy. Yeah? There are some models around in the Bayesian nonparametric literature which are actually not in this class here. So for example, there's in the 1970s, after the Dirichlet process was first introduced, people tried to come up with generalizations along several lines. And one of them is something called a neutral to the right process, which is some form of Levy process essentially. I'm not going to tell you exactly what that is, but it's basically, it's a class of models which contains the Dirichlet process as a special case. It has some nice properties. And one thing you can show about it is that it's conjugate in the sense that if you take the posterior of a neutral to the right process, it's again a neutral to the right process. But it is not conjugate in this sense, so you know it's a neutral to the right process, but you don't know which one. okay? And you need to find some other way to figure that out. So that is not very useful, yeah? Okay, so what we need is this, basically we need to construct models that have this kind of conjugacy, and then we don't need a base equation, okay? That is not to say that this is the only way that we can possibly substitute for a base equation. There may be many others, but this is the only one, or pretty much the only one, the only analytic way at least that I know about, and that is in any way used in the nonparametric Bayesian literature. Okay, so when we construct nonparametric Bayesian models, we basically have to try and make sure that they are conjugate. How can we do that? Well, one thing is we are reusing components, right? We use build hierarchical models, for example. And in that case, if we use models that already are conjugate, then we can handle the individual layers of the hierarchy, and then if we do Gibbs sampling, we're good. Okay. So basically, the way to utilize this in hierarchical models is use components which have this property. Yeah? It's also possible to show that if you use these constructions that I showed you before, these projective limit constructions that we used for the Gaussian process and the Dirichlet process over the last half hour, yeah? That if you use marginals which are conjugate, which have this property, then under suitable conditions, the model that you get out is again conjugate. So in this sense, the Dirichlet process is conjugate because the Dirichlet distribution is conjugate. Yeah? And the Gaussian process is conjugate because the Gaussian distribution is conjugate. And since conjugacy in parametric models like the Dirichlet and the Gaussian distribution is something that occurs up to some borderline cases only in exponential families, you have a rough rule of thumb that models which have this property are basically models that you can get as projective limits of exponential family models. Okay. So like the Gaussian, like the Dirichlet, and so on. Okay. So much for the representation problem. And now the final thing that I would like to talk about in the context of how we can construct models is exchangeability once again. And I'm just going to quickly review the two slides on exchangeability that I showed yesterday. But the real question here is if we want to build a model for data that does not come as a sequence, then what can we do? Yeah? What can we use to substitute for exchangeable sequences? Okay. So, quick reminder. Exchangeability, recall that exchangeability was the kind of property that we use to characterize the case where we can make this assumption here that the data that we see is decomposed into a pattern and independent noise. Right? So the pattern was our parameter, and the independent noise is basically given by the likelihood. Given the parameter value, how does the data in this case scatter around the parameter, which is the red line? Right? Okay. And I told you that if we have this exchangeability property, so if the order in which the data comes in does not change its distribution, does not change its probability, if the order is irrelevant, then we have this property. And I showed you this this integral representation here of Definetti's theorem, which expresses exactly this conditional independence, right? This is in the context of mixture models. We also saw yesterday that mixtures are two-stage sampling procedures, right? First sample from the mixing measure, and then sample from the component. This is exactly what you see here, only in this case the mixing measure is the prior, and then the component is this distribution of an infinite IID sequence, right? So you can in this sense you can interpret all Bayesian models as some form of mixture. You can also see you can also regard these hierarchies that I showed you earlier as repeated mixing, if you will, yeah, from a technical perspective. Okay, but really the important bit here is we have an invariance property, which is this invariance of the probability of the data under permutations, and that gives us a conditional independence property. Okay, and I'm now going to show you two examples of where we get this kind of, where we have this kind of principle. We also have an invariance property or kind of permutation invariance property, and we get some form of conditional independence property that we can use to build Bayesian models. But the data is now a more sophisticated random object. Yeah. And the first one is the case where we have random partitions. So that is something I already mentioned briefly yesterday. If we have a random partition, in which case can we assume that this random partition comes from a discrete random measure, right? This whole setup we looked at yesterday in clustering was we generate a discrete random measure, use it as a mixing distribution in a mixture, and then sample our data from that. And that is how we explain how the clustered data is generated. In what cases can we assume that that is really true? Yeah. Okay. And the result which addresses this is something called Kingman's theorem. So Kingman's theorem is the random partition version of Definetti's theorem. Okay. And the objects that are involved here are the following. We need to remember in Definetti's theorem, I told you that this random object that we draw here, that is a probability measure, right? We have a random probability measure, we fix that measure, and then we sample IID from that measure. Yeah? And now here, the random object is a partition of the unit interval. And what is this? If you think of the discrete random measure, the length of these intervals here, these are exactly the weights that describe the cluster sizes. Yeah? So you see here, this is the unit interval from 0 to 1. Yeah? And then we have subdivided this interval into subintervals. The lengths of these intervals sum up to 1, or to something smaller than 1 possibly, because you can see that I left like a little free part here in the end. So I rank ordered them, right? They are arranged in decreasing size. Yeah? And then here is a little bit free in the end. So the reason for that is following. If you have a random partition of n, think again of clustering. We take an infinite data set, and the data points are indexed by order of occurrence, right? 1, 2, 3, 4, 5, and so on. And now we partition the data, we cluster the data. That gives us a partition of the index set. And this here is, so n is the index set. These are indices of data points. And now we partition that into clusters. Okay? And now we assume that this partition here is exchangeable. So once again, an exchangeable partition means the probability of the partition. That only makes sense for a random partition, right? Fixed partition, exchangeability, it doesn't have a meaning. So for a random partition, if we swap points or values between blocks in the partition, it doesn't change the probability. And another way to express that is the probability of the partition depends only on how large the blocks are, not what elements are in the blocks. Yeah? Okay, so we have a random partition of n, and it's exchangeable if and only if it has a representation like this. So this looks kind of like the Definetti integral, right? But now we don't have, down here we have some distribution which is no longer a factorial, because we're not dealing with an IID sequence. We have to, this has to be a partition in some sense. And how do we generate this? The object which tells us how to generate a partition that characterizes the random partition is exactly this. And the way we sample from it is we draw an infinite sequence of uniform random variables. Yeah? So instead of drawing the data directly, x1, x2, x3, we draw uniform random variables u1, u2, u3, and so on. And then we throw them on the interval. Yeah? So the uniform random variables are just uniform on the interval. And that associates each number, right, 1, 2, 3, with a point in this interval. Yeah? And what this here simply says is, this here is the probability of the first cluster, this is the probability of the second cluster, and so on. Here, point 1 and point 3 are in cluster number 2. Point 2 is in whatever cluster this is, and so on and so forth. Yeah? Okay, and now why did I leave this this gap here at the end? You can show that that a random partition is exchangeable if it has a certain, if it is exchangeable, it needs to have a certain structure. Yeah? And it cannot have finite blocks that contain more than one element. Okay? So either the blocks are infinite, and if you take an infinite, you can think of these proportions here in the following way. Say you have a partition of n numbers, yeah? Then you can look at the sizes of the blocks and normalize, divide them by n. Yeah? So then these block sizes will all add up to 1. They're positive numbers, they add up to 1. Now you make n larger and larger, and you get limits of these block sizes. Okay? And the limits are exactly these ratios here, these numbers between 0 and 1. And now if you have finite blocks, then the limit is 0, right? If you have a block that has finite lengths and divide by n, you make n larger and larger, that goes to 0. Okay? So you have, we have this mass here, which corresponds to blocks which are infinite, but have this proportion of the overall number of elements. And then we have finite blocks, which correspond to this little bit here. Yeah? And individual numbers are basically all 0, but this is the total amount of numbers that are not in infinite blocks. Okay? All right. Good. So if you define a sampling rule for a partition like this, yeah, this gives us the probability of a random partition parameterized by a subdivision of the interval. Yeah? And this is now the analog of this formula. Yeah? So the parameter we sample, here it was a random probability measure, we sample IID from that measure. Now what we sample here is this parameter is a partition of the interval, and the analog of IID sampling is throwing uniform random variables on this interval and interpreting that as a clustering or as a partition. Okay? Good. And then if we do that, you can see that this kind of sampling scheme really corresponds to a discrete random measure. Yeah? The way we sample from a discrete random measure is we sample components in proportion to these probabilities here. And then the only difference is that we don't throw just these uniform random variables at it, but rather we associate each of these components with a parameter value, right? That's an extra information that we have. Yeah? So this here is the weight part of the discrete random measure. Okay. So that way we can generate random partitions in a two-stage sampling procedure. Okay. Okay. So this is kind of course, this is kind of just clustering models revisited, right? I motivated this by saying, okay, we want to build models on new types of data, and now what I showed you is just the type of data that we talked about yesterday all day, right? So let me show you one example of something that is not really widely used, but it certainly will be. And this is the case where the data is a random graph. Okay, so our observations form a random graph, and it's not that we get a sequence of random graphs. In that case, we could just apply the Finetti theorem, right? Because we could say, okay, we have a sequence of random graphs. Each observation is graph valued. Put distributions on graphs and see whether the sequence is exchangeable. But here, rather, what we look at is observations. Say we have a graph which is defined on a set of nodes, right? And now observations are links between these nodes. And so as more and more observations come in, they aggregate into a larger and larger graph. Yeah? So corresponding to a sample of size n, in this case, is a subgraph of size n on n nodes. Okay? So we have one astronomically large graph, and we see a snapshot of it. As we see more and more observations, the snapshot gets larger. It's not multiple graphs. And now we want to ask whether we have, what is the notion of invariance on this graph, and does it give us something like the Finetti representation? Yeah? And what is the random object that underlies the graph? In the sequence case, it's a random measure. What's the random object that underlies the graph? Okay. So the theorem which does this is called the Aldous-Huber theorem. And the way this random graph is, so the notion of invariance that we need is, again, exchangeability. And in this case, exchangeability means we are permuting the nodes of the graph. Yeah? So imagine that we have an infinitely large graph, and the nodes are labeled by by natural numbers, 1, 2, 3, 4, and so on. And now we say that, so that is the random graph, and we say the probability of this random graph does not change if we relabel the nodes, if we just change the node labels, interchange them. And intuitively what that means is that the probability of this graph depends on which kind of edge patterns occur how often. So how many single edges do you have, how many triangles do you have, how many squares of edges, and so on. Yeah? But it does not depend on where these patterns occur, just how often. Yeah. Okay, and now it turns out that the random object with which you can summarize this is a function which is defined on the unit square and maps to the unit interval. Yeah? So I drew the unit square here, and this is the unit interval. And the way we interpret this function is, so this function takes 2 arguments, and then it spits out a probability. Yeah? We interpret this here as a probability. And now we need a sampling rule for generating this graph at random. Yeah? How do we generate it? We generate it by first sampling a function like this at random. Yeah? Then we fix that function, and now given that function, we sample the graph. How do we sample the graph? For each edge. So first of all, we draw an infinite sequence of uniform random variables. They are indexed 1, 2, 3, and so on. So each of them corresponds to a node with the corresponding index. Yeah? And now how do we sample the edges? For each pair of nodes, we want to know whether there is an edge. We take, so nodes I and j, we take the corresponding 2 values, I and j here. Yeah? That's a point on the unit square. We plug that into this function, and this function gives us a probability. And then we flip a coin with that probability and say, okay, if that comes up heads, the edge is there. Otherwise, it's not. Okay? So you can see that this makes, given, we were talking about conditional independence, so given this function here, all the edges are independent of each other. Right? But only given this function, and of course, the sequence of uniform random variables. Yeah? So if we have sampled up to this stage here, then all the edges are conditionally independent given what we have already seen. Yeah. In the previous stage here, in this case here, once we have seen this subdivision, once we have sampled that, the elements of the partitions are conditionally independent of each other. Okay? All right. So, and then you can write that if you look at this sampling procedure and regard it as a distribution which is parameterized by the function, right? Then you can write it in this way. So this is the probability of the graph given the value of this function. Then you can again write that as an integral representation of this form. Okay. So you can see what the underlying theme here is. The underlying theme is that if we want to do Bayesian modeling and we want to we need a conditional independent structure like this to justify this assumption that we have an independent randomness part and some form of common information, joint information that we can extract by statistical inference, right? And we need some kind of, and the way we can get that is by looking at some form of invariance, in this case under permutations, and then finding a representation like this. Yeah? I can tell you it's not easy to find these representations, but fortunately probabilists are doing most of the work for us. Yeah? So we don't actually have to do it. And there's a whole bunch of these theorems already around that we can use for different types of data. Yeah? So if we have basically sequences of points, then we have De Finetti's theorem. If we have sequences in the sense of time series, which in some sense evolve over time, yeah? There's a theorem by Diaconis and Friedman which says that that such sequences under a certain invariance condition are mixtures of Markov chains, right? So here we have mixtures of IID sequences. In the exchangeable case, here we have Markov chains. In the case of partitions, we have the theorem by Kingman, which says we have these so-called paintbox partitions. That is what Kingman called them, but it's basically sampling from these cluster weights. Yeah? If we want to look at graphs, or then there's this Aldous-Huber theorem. This is actually more generally applicable to arrays. And the idea with arrays is you can think of a graph as a matrix, right? It has an adjacency matrix, and now you can think of making this matrix which is a two-way array, you can make that a three-way array, and so on. Yeah. Okay, and just to close up this topic, there's kind of like an underlying mathematical theory here, which is the theory of ergodic decompositions, and this is really one of the most, in my opinion, one of the most stunningly beautiful topics in probability. And what it basically gives you is you have so the basic common theme is you have a probability measure, and it has an invariance property. That was what we saw was exchangeability. Yeah, different forms of exchangeability on partitions, on graphs, and so on. But we express this exchangeability by saying it's invariant under permutations. Now, permutations are a group in mathematical terms, yeah, and there's a lot of groups. And what groups express in mathematics are different forms of symmetry. So you have permutation invariance, which is a form of symmetry. You can have rotation invariance, which is spatial symmetry, and so on and so forth. And the basic theme is you have a probability distribution, and it is invariant under some form of symmetry, which is formalized by a group, and that gives you an integral decomposition. Yeah, it's totally awesome. Okay. So much for that. So this is like, basically, if we want to construct new Bayesian models on new types of data, then for a given type of data, we first have to solve some fundamental questions before we can really start modeling or designing specific models. But we don't have to do this over and over again for each model we want to design, right? We just have to do this once for this type of data, for, say, graphs or for permutations, for partitions and so on. Yeah? Okay. Okay, after all these applied topics, let me get to something more theoretical. All right, so what I've talked about so far is different forms of modeling, right? Modeling, and a little bit yesterday about applications. And there's a different line of work that is happening in mathematical statistics, where you don't ask the question, how can we build new models, but you rather ask, if for the models that we already have, how do they behave? Yeah? And what statisticians always want to know is if I see more and more samples, how quickly does the model converge to the right parameter value? Right? How quickly how much data do I need to estimate my parameter or to get a good posterior? Yeah? And in about the last 10 years, some very good mathematical statisticians have started to applying this idea, or rather ask this question about Bayesian nonparametric models. And actually that is quite remarkable in the sense that just because some of the people who are involved in that are really famous, it is making Bayesian nonparametrics very fashionable suddenly with people who were not interested in it before. But there are some really neat results here. And I just would like you to know roughly what questions are being asked in this area, and what kind of results, or what is kind of involved in formulating these results. Yeah. Okay, so what I've drawn here is a cartoon of the set of probability measures. Yeah. It's in this case, this would be actually the set of probability measures over 3 possible events. Yeah. So like say a coin with 3 sides, or like say a coin with 2 sides and it can land on the edge. Right. This is heads. This is tails. This is no outcome. And now you can imagine that if you have a 4th event, then you would get something like a tetraeder. Right. This is a simplex. This is the domain of a Dirichlet distribution, if you will. And if you add more and more events, in the general case of probability distributions is usually infinite, then you really get something that is, the closest description is really something like a triangle, only in a very high dimensional space. Okay, so every single point in the set here is the probability distribution, and the corner points The extreme points are probabilities on a single event, which place all their mass on a single event. Yeah? And now what is a model, a statistical model? A statistical model is a family of probability distributions, right? Like the family of all Gaussians. Yeah? So you can imagine this here to be the set of probability, represent a set of probability distributions on the real line. And then the set of all Gaussian distributions would be some subset of that. And I've drawn that here in blue. Yeah? So that is some subset of the set of probability distributions. And then if we have a particular, some particular model is a single point in here. Okay. All right. And now let's say P0 here is the distribution that actually has generated our data. We don't know which distribution that is, but there's some true distribution which has actually generated our data. And now we try to find this distribution by positing a model and then estimate the model parameter from the data. And if we have chosen the right model and if our estimator is good, then as we see more and more data, we will get closer, the estimate that we get will get us closer and closer to this true distribution. That is a very basic idea of statistical inference. All right, now, so what can happen if we choose a model? Then that is an assumption, right? That's a modeling assumption. And one thing that could happen is that we get lucky and the true distribution is actually inside the model. Yeah, that's good. And then there's another case, which is the true distribution is outside the model, and in statistics this case is called misspecification. Yeah, so we say that the model is misspecified if the true distribution of the data is not inside the model. And now you can ask, in either case we can ask if we see more and more data, how quickly does our estimate converge to the true model? How much data do we need to get a good estimate of what the real distribution is? And in this case we can additionally ask what, since the true distribution is not in there, how is the estimator going to behave? Yeah? So what we would certainly like to see in this case is that our estimate, the estimate that we get is something that's over here, that's as close as possible to this rather than something over here. Of course, we have to define what close means in this space. But okay, so, and this is in one of the more from a theoretical point of view, one of the motivations for using non-parametric models, because essentially if we just quickly go back to this picture, this is an infinite dimensional space, right? And if we use, say, a Gaussian, the family of Gaussians as a model, then a Gaussian is characterized by a finite dimensional parameter vector, so it has a finite number of degrees of freedom, right? It's a parametric model, it has a finite number of degrees of freedom. So it is a finite dimensional subset of this space here. And a finite dimensional subset of an infinite dimensional space is small. Yeah. So we don't have it will be difficult, or in general, if we don't know what the true distribution is, then it will be difficult to get close to the true distribution. The idea is, if you want to make your model more flexible, that means if you want this model to spread out more widely over the space and be closer to any possible distribution of the data, then you have to use a non-parametric model. Yeah? You can't do that with a finite dimensional parameterization. Okay. Good. Now, if you do parametric statistics or parametric Bayesian statistics, and you have to choose a prior, and you don't know anything about what the parameter should look like, then of course what you will usually do is choose a uniform prior, right? That's maximal uncertainty. Now, if we don't know anything about what our model is here in this case, then we would also like to choose something like a uniform prior, something that spreads out evenly over the whole space. But as I mentioned earlier already, this space is infinite dimensional, and on infinite dimensional, these uniform distributions just don't exist. Yeah. So we need something else. Okay. Let me just at this point say a few words about the interpretation of prior assumptions in Bayesian nonparametrics, because they are a bit different from the prior assumptions that we make in parametric statistics, or the technically it's kind of the same thing, but the interpretation comes out a little bit differently. So in parametric statistics, if you say put a prior on a Gaussian, then the prior assumption is the mean of my data, something that says the mean of my data is probably going to be over here. Yeah, that's what putting a prior on a Gaussian expresses. Whereas in these non-parametric models, what you express by the prior assumption is typically a more structural property. So, for example, in the GP regression model, we saw that if the unknown parameter is the bandwidth of the Gaussian process prior, if we don't know the bandwidth of the Gaussian process prior, or if we choose the bandwidth of the Gaussian process prior, then we can sample any continuous function from that model, and the prior assumption says it will probably oscillate at a certain rate. Yeah, it will probably have a frequency roughly in this range. That is our prior assumption. And in remember what we talked about yesterday in clustering, we if we choose, for example, if we choose this Chinese restaurant process prior or Dirichlet process prior, then our assumption, the prior assumption that encodes is how does the distribution of cluster sizes behave. And the Dirichlet process encodes the assumption the number of clusters is distributed logarithmically in the number of data points, right? It's an assumption on the decay of these cluster weights. And if we believe that, for example, that we have, so if we believe we have a small number of clusters, then that is maybe a good choice, yeah? And if we believe that the clusters follow, the distribution of clusters follows the power law, then we would instead use a Pittman-Yaw process, for instance, yeah? Okay, so let me just see how much time I have left. Okay. All right, so these kind of results that that people like to, or that mathematics statisticians are interested in to quantify how well behaved these models are. There are basically two types of properties that people are interested in. One is a property called consistency. And roughly speaking, what consistency means is, am I going to recover the right value of the parameter, supposing that I have an infinite amount of data? Yeah. So in parametric statistics or parametric non-Bayesian statistics, consistency simply means that the estimator is going to converge to the true parameter value. Yeah? Now, in Bayesian statistics, we're not actually computing an estimator, a point estimator, but what we want to compute is a posterior. So we have to formulate what it means for a posterior to converge, and basically what that means is that the easiest way to think about it is simply that the posterior, as we see more and more data, becomes more and more peak, right? And that in the limit of infinitely many data points, it will become a delta peak at a single point, and that should be, if it's consistent, that should be the true parameter value. Okay. Okay. So there's now there's a simple definition of consistency in Bayesian models, yeah, which is the following. There's a problem, I tell you in advance, there's a problem with this definition. So this definition has been used for a long time, and it's the following. If we assume that we sample the data from a specific distribution which has parameter value theta naught. Okay? So theta naught is the true parameter value that has actually generated the data. If the posterior converges to this true parameter value with probability 1 under the prior, then we say that the model is consistent. Why do we have this extra with probability 1 under the prior here? If you sample from a Bayesian model, then remember we do two-stage sampling. We first sample a parameter value from the prior, then we plug that into the likelihood, and we sample IID from the likelihood, and that is the way we generate our data. Okay, so now what we have to ask here is, if we say the posterior converges, okay, we can take this data that we have sampled, we can compute a posterior from that, but what it will converge to depends on which parameter value we have drawn from the prior, right? And hopefully it will converge to that actual value. Yeah? And this definition here says it always has to do that, except for some parameter values as as long as that has probability 0. Yeah? That seems perfectly safe at first glance. Yeah? So, as you know, there are in probability, it is possible for a set that is not empty to have 0 probability. Right? For example, a single point under Gaussian always has 0 probability. Any finite set under Gaussian always has 0 probability, and so on. And what we're saying here is simply it's okay if there are exceptions for which this consistency does not hold, as long as the prior says these exceptions are never going to occur. Right? Now, what is the problem with that? The problem is that simply saying, I mean, basically the prior may be wrong. Right? If, for example, if we have a model like this, if you look back at this cartoon here, so if this is our model, if these are our possible likelihoods, then in a Bayesian case, this would mean that the prior puts probability mass on 1 on this set here. Right? What we can sample from the prior are only the parameters for our model. If we put a prior on Gaussians, then we're going to end up with a Gaussian with probability 1 in the likelihood. So all this huge set out here, everything that's gray here, all of that together has probability 0. Yeah? And that is a pretty damn large set of exceptions. Right? So in particular, in this misspecification case, if the true distribution of the data is not actually in our model, is not covered by our model assumption, then we can be arbitrarily wrong here for all these possible models. But this definition still says it's consistent. Yeah? The estimation process is consistent. So now why do I show you this definition if it's not a good definition? Basically because this definition has been used for decades as a definition of consistency in Bayesian statistics. And because this definition is so weak, you can prove very general, very strong results based on this definition. Yeah? You put in very weak assumptions, what you require for consistency is very weak, so you can prove results that basically say you're always consistent. And that is creating a lot of confusion because this consistency does not actually express what we would like it to express. Yeah? So there is a theorem which goes back to the famous probabilist Joe Duke, and it says under some very mild conditions, which essentially in statistical terms refer to address identifiability of models, Bayesian models are consistent in this sense. Okay? And so there is kind of a folklore in Bayesian statistics that if you're a Bayesian, you don't have to worry about consistency. Yeah? But that is only true if this definition is good enough for you. So now here's a stronger definition of consistency, and this is kind of, you know, since this definition is modified to express what frequentist statisticians, who usually care more about consistency, what they would, you know, it's tailored to the way they think about consistency, and that is why people sometimes call it frequentist consistency of Bayesian models. So what it says is a Bayesian model is consistent at a given distribution. So for some true distribution of the data, the Bayesian model is consistent if under this distribution of the data, it converges to the true posterior. Yeah? So we don't have these exceptions anymore. So instead of asking what happens at a random point, which is however sampled from the prior, we ask what happens at a specific point. Okay? All right. And in this case, you know, in this case, results become much more nuanced. They are much harder to prove, but they also tell us a lot more about what these models really mean and how they behave. Yeah, these results are just much more useful. But it's not this simple case here where everything is basically covered by one simple theorem. Yeah, but you really have to input a lot of technical know-how to prove these results. Okay. All right. So I have about 2 minutes left, and I have 2 slides left, and I think I spoke about this slide for about 15 minutes or so. So that is not going to work, and I'm going to end here. Thank you very much. Questions?
Why some popular, I don't know remember for sure, but there are popular construction of country example that Bayesian nonparametrics cannot be consistent.
Yeah, right.
By Diaconis.
Yeah, so exactly. Diaconis and Friedman have an example of a Bayesian model that uses a Dirichlet process and is hopelessly inconsistent. So basically, no matter how much data you see, it always will get everything totally wrong. Okay. However, it's really it's an absolutely pathological example, and in particular in the way that we use the Dirichlet process in machine learning for clustering, that will never happen. Okay. So these models in machine learning, when we use the Dirichlet process, remember we use it as a distribution in a mixture, right? And these Dirichlet process mixture models are pretty well behaved, yeah, in a statistical sense. It's only if you use the Dirichlet process for things like density estimation that these problems occur. But using, if you have something that's drawn from a smooth density, and then you use a prior that was probability 1 produces something discrete to approximate the smooth density, then you can't really be too upset if it doesn't work out, right? So, but you're right, and so there was this counterexample, and it's in hindsight we might say, okay, that's kind of obvious that has to go wrong or something like that, but it was very important because what Diaconis and Friedman really wanted to point out was the weakness of the theorem. So they came up with an example which was obviously a really stupid way to do things, right? But it satisfies this notion of consistency, and it behaves in a way that is, that nobody would possibly call consistent. Yeah. But under this definition here, it actually is consistent. Yeah.
What is a true distribution?
What we mean by true distribution?
Yeah.
It's simply if we compute our estimates from a given set of observations, right? And the true distribution is simply the distribution from which these observations were actually generated.
So how does it relate to objective subjective Bayesian distinction?
Okay, so basically, first of all, so objective, subjective are different ways to approach the choice of priors, right? So you can think of that maybe, I mean, they are philosophically tainted, but they're basically design principles, right? But there is this subjectivist point of view in Bayesian methods, which is that so as Definetti wrote, that probabilities don't exist; they're only beliefs, yeah, or there's only uncertainty. And that is this idea that, so I have heard people basically use this idea of subjectivism to defend this definition here. And the idea is, there's no truth, there's only your prior. Yeah? And if you get your prior wrong, then, well, okay, right? But I think that is very short-sighted, because I mean, even if you subscribe to this idea of subjectivism, then you still have to take your prior beliefs and translate them into something technical, right? Into a prior distribution. Now, if you say, okay, I believe this and this and this about my nonparametric model, I mean, we have just seen how difficult it is to construct nonparametric models. How do you turn that into a probability distribution? In order to do that in a proper way, you have to know how these different probability distributions that you can choose, how they behave. And in order to know how they behave, you have to be able to ask these what-if questions, and which tell you, okay, if I get it wrong, then what is going to happen? If I get it wrong in this way, then what is going to happen if I get it, and so on and so forth.
Priors become, instead of placements, structures in nonparametrics.
Well, yeah. So that is another point. But you can interpret things. I mean, I think it's useful to think about nonparametric prior assumptions in this sense. But you can still get them totally wrong, right? Like, for example, this example that was was just mentioned in the other question was a Dirichlet process using a Dirichlet process for density estimation. Basically, the prior assumption that you make, you know that you are fitting, or you at least have to expect that the data that you are trying to fit comes from a continuous distribution, and the prior assumption that you make is my distribution is discrete. Yeah, that is a structural assumption, but it's still wrong.
So we can think of it through structure, maybe, or something.
Yeah, I think it's often useful to try to think of it as a structure, as a structure or the nature of this pattern that is underlying the data. Yeah.
In the example for the random partitions, you chose uniform distributions up to some fixed parametric or value for a particular interval for the weights of the partition. So why did you choose uniform distributions when you said that in non-parametrics it doesn't cover the space very well?
Okay. There's two. So there are several different distributions involved here, and the uniform distribution that we're using here is simply a device to generate to associate these indices with a cluster. Okay. So in other words, this partition of the interval really specifies our distribution over the clusters, and we sample from that by using the uniform distribution as a device. Okay? So we sample from this distribution by first drawing this infinite number of uniform random variables, throw them at the interval. But this is a sampling procedure that defines another form of distribution, and the other distribution that we're really sampling from is parameterized by this partition. Okay? And then the other issue is that this here, what we have done here, when we look at that, this describes only in say, the Dirichlet process case, this describes only what happens according to the weights of the clusters. But it doesn't tell us anything about the parameter values that we sample from the clusters. So in the random measure point of view, in the Dirichlet process point of view, we have these two parts of information, and here we have simply thrown out one of them. Yeah? But basically what this says here is that if we have random partitions that are exchangeable, then we can separate these two problems. We can sample from the cluster weights in this way and treat the locations of the clusters or the parameter of the individual cluster components in